So, section 14.1, double integrals. So the goal in this section is to introduce notation. And also a method of evaluation. So, and also I guess, and the meaning. So what I'll do is I'll begin by just doing a brief review of what a single integral means. So recall in Calc 1, a single integral generally is understood as representing area under a curve. So let's say area under f of x. So a picture for this, and the picture will be immensely helpful when we go to two variables, is you've got a function, something like this. I'm going to label my axes. And then what you have is you have an interval. So what I'm going to do is I'm going to shade the entire interval. That will help. And then what you do is you find the area under f of x by doing the integral from a to b of f of x dx. And what this gets you on the picture, as you know, is it gets you this. So this guy is this guy. And then this integral just gets calculated using standard methods. This guy you calculate as you know. Doesn't mean it's easy, but there we go. So the analogy now. Is as follows. So I'm going to draw a little arrow here. We'll see why in a second. So suppose now that we have a function f of xy. And that's going to be defined on a region in the xy plane. So picture for this. So as we go through this, take a look at how the pictures are very similar to one another, in a sense. So we've got the xy plane down here. Then we have a graph, so think about like a paraboloid, something like that. So this is on f of xy. Then what it happens now is down in the xy plane we have a region. This r is in the xy plane. And then the analogy here is that we get a volume. And this volume is above the region and below the function. So if you take a second look at these two pictures, we both have a function in both. We have an interval on the left and a region on the right. On the left we get an area, on the right we get a volume. So suppose we wanted that volume. So what we do is we represent it by a double integral. So this volume is represented by the double integral it's denoted by a double integral over r of f of xy dA. Now, that's great, but it doesn't tell us how to evaluate it. So this big question is, how do we evaluate this? Now, a couple things about this integral. The dA is just a thing that needs to be there. Don't worry about why it's there right now, but it is. And we'll sort that out in a minute. So the next question then, of course, is like, well, how do we, if we see the parallels between these, how do we evaluate the integral on the right? What do we do with a thing that looks like that? So what we'll do first is we'll actually sort of punt the problem, look at something that would seem completely different, which will be double iterated integrals. So this word iterated, all this will mean is that it has limits of integration. You could think of it as a definite integral if you like. So an iterated integral, iterated double integral, is nothing more than basically one single integral nested inside another. So an iterated double integral is one definite integral nested inside another. Now it's a little more nuanced than that, but that's okay. So one point is that one of them is with respect to x, the other is with respect to y. This will change in the future, but this is good for now. And the second rule, which will be a bit more confusing, is that the inner limits of integration may contain the outside variable. This second point may make absolutely no sense right now, and that's okay. So what we'll do is we'll look at a couple of examples. So this is the key point to look at first. One will be with respect to x, the other with respect to y, and then we'll look at this other point second. So one might be, say, 0 to 1, 1 to 3, x, y, dx, dy. So if you look at what we've got here, we've got the inner one is with respect to x, and then the outer one is with respect to y. So this is basically just a thing to evaluate, and all we do is we evaluate from the inside out. So the inside goes first with respect to the inside variable. So what we do here is we get something like this. We integrate with respect to x. The outside integral just goes along for the ride. So when we integrate this with respect to x right here, y is the variable. So we get 1/2 x squared y, 1 to 3. So these variables get plugged in for x, because that was the variable we integrated with respect to. So I get 1/2 3 squared y minus 1/2 1 squared y dy. This will simplify it a bit, so I get 9/2 y minus 1/2 y, which is 8/2 y, which is 4y. That gets integrated with respect to y. and then I plug in for y, I get 2 times 1 squared minus 2 times 0 squared, and that's 2. That's our final answer. Don't worry about what that represents, just look at yourself as like a little machine that worked it out. So let's look at another example. So I'll do 2 more. So for the first one, let me just switch the variables around. So something like 0 to 2, 0 to 1, say x plus y, and then I'll do, say, dy dx. So here the innermost integral is with respect to y. So that's the one we do first. So the outside integral goes along for a ride. So when we integrate with respect to y, the x is the constant. So we get x, y plus 1/2 y squared. And then those get plugged in for y, because y is the variable. So when we do that, we get x times 1 plus 1/2 1 squared minus x times 0 minus 1/2 times 0 squared. The zeros aren't really necessary here, but I'm going to be complete. So then we get x plus 1/2 dx, and now we're basically back in Calc 1 territory. So I integrate plug in, and that's it, because plugging the 0 gives us nothing new. So that's our answer. So for the last example, just take a look at this one. So this will illustrate this second point, that the inner limits of integration may contain the outside variable. So I'll keep this really nice and simple. 0 to 1, 0 to 1. Oops, that is not what I meant. Let's say 0 to 1, 0 to y, x dx dy. So what I want you to see here is that the inner limits of integration may contain the outside variable. This is okay. So when we evaluate this, you'll see why this is okay, because we integrate with respect to x first, because it's the inside variable. We get 1/2 x squared 0 to y dy. We plug those in for x because that's the variable. And when we do that, we just get a nice integral of y. Nothing tremendously weird happens. And then we integrate with respect to y, and everything is lovely. So for now, like I said, don't worry about what any of these integrals mean. Just notice you have one integral nested inside the other. You integrate the inner one first with respect to the correct variable, and the outer one with respect to the correct variable. At the end of the day, you will, so here, we'll put this in red. So notice you will always get a constant. May not be pretty, but it's always a constant. So think about the two things we have so far. We have the sense of a double integral giving us a volume. Then we have this double iterated integral, which is just this thing that we calculate that gives us a number. So one sort of clear question is, what's the connection between these two? So here's the deal. Evaluating double integrals. So this will go as follows. So to evaluate one of these guys, remember this represents volume under f. What we do is we convert it into a double iterated integral, one of these things we just did. and then we can just evaluate. So the question, of course, how do we do this? And the answer is it will totally depend upon the region. So it will depend on R. So just to reflect upon what that R is before we dive in. Remember, this is our situation. The R was the region down here. The volume we're looking for is this. And note the function is this. This is our f. So at the end of the day, the point is that what we will do is this will be critical. This R is everything. So it'll depend totally on that. And so what will happen is we'll break it down into two different possibilities in this section. And then later on in the chapter, we'll introduce a third possibility. But the thing to remember is focus on that R. That R is everything. All right. So the way this will work is we'll look at two different possibilities. So possibility A is that R is vertically simple. Now we'll need to define what this means and talk about how that changes things. So vertically simple actually is a description that you know, but you don't know the term. So what we'll do is we'll define this first. So definition. So R is vertically simple which I'm going to abbreviate VS, if it can be described as follows. And I'm going to do this with a picture. So a vertically simple region, remember this is the R that we're describing. This is in the XY plane. So a region is vertically simple if it can be described as being between two functions on an interval. So we've got an A and a B on the x-axis. We've got a bottom function. We've got a top function. And we've got our R, which is right between these. So if this is the R, and then I'll explain what happens if this is the R, and then we'll look at a couple of examples. Right, so if R is vertically simple, then if you are trying to evaluate this integral, then what happens is this becomes a double iterated integral. The outside limits of integration are A and B. The inside limits are the bottom function and the top function. The f of xy just sits inside, and we have dy and dx. Now stop and have a think for a second, because this makes sense in the sense that the dx's correspond to the dx integral, and the top and the bottom correspond to the y's, because these guys are y's. So the top and the bottom are y equals, and the left and the right are x's. So once we get it into this form, of course, we just evaluate according to the previous number. And simply evaluate. I should put simply in quotes because it may be icky. As previous. So let's take a look at a nice simple example. So consider this example. So I'll keep this really, really nice and simple. I'll just give you the R. So the R could be something like the following. So I'll draw it in red. So say something like, this would be the line y equals x. This will go out to say 5 from 0. Bottom line will just be 0. That's the R. And let's suppose we want to find, say, the double integral over R of, say, x dA. Now, one thing to note here in this problem is that this x, this is a terrible example. Hold on, let me modify this very slightly. Let me make this an x squared. So the point I want to make here is that in this problem, the x squared is not on the picture. Remember, the x squared is the function that we're finding the volume under. All right, what's really going on here is this. The picture is the picture of the R is the region that we're focused on when we're evaluating. So we'll look at some more sophisticated examples soon. But the key point here to see is that this R is vertically simple. Right, because it's between A equals 0, B equals 5. Top is y equals x. Bottom is y equals 0. So this double integral turns into a double iterated integral. Just like that. And then of course we can evaluate this thing as we did before. We can integrate inside with respect to y. X is the constant. Can plug those limits of integration in for y, because that's what we integrated with respect to. When we do that, we get 0 to 5 x cubed. We get 1/4 x to the 4th, which is then 1/4 times 5 to the 4th, and that's the solution. So the thing to notice here is we knew what R looked like. It's vertically simple, top function, bottom functions, constants on the left and right. That allows us to evaluate things, get things worked out. So we've got vertically simple. This has a parallel in the other direction. So let's take a look at that. So now we'll look at what's called horizontally simple. So this is similar, but it's a bit weird because of the way we look at the functions. So we'll say a region R is horizontally simple. Which I'm going to write as HS if it may be described as in the following picture. So just like before, I have a region, but the difference here is that the constants are going to be on the y-axis. Let me be careful to label. So these will be C and D, let's say, and then we have these functions which don't look like functions, but they're functions in the sense of there's like a right function and a left function. And we have a region that's between those two up in here. So these functions, these are of the form x equals, not y equals. So what happens here is if R is horizontally simple, you can probably guess what's going to happen. Then if I'm doing a double integral over R of f of xy dA, then the outer integral will be the y's, CD. The inner integral will be the left and right, and the left goes lower and the right goes higher. And then we have our f of xy, and we have dx dy. And again, this makes sense because the x's are the left and the right, and the y's are the outside integral. These are y values. Then, of course, just evaluate. So let's look at an example of this. So let's take a look at an example. Right, so let's suppose r is given here, and I'll give this r a little more confusing than the previous r. So let's say r looks something like, say, this would be the line y equals x. This would be the line y equals 1/2 x. We'll go between, say, y equals 0 and y equals 5. That is the r. Now, one thing to note is that if I think of this horizontally simple, what we have is, it's a bit easier to see if I rewrite it. So I'll note. So if here's the region, let me just redraw it so I can relabel it. So this is the right-hand function. This is y equals 1/2 x, which we can think of as x equals 2y. And this is the left-hand function, which is y equals x, but we'll think of it as x equals y. I know there's not much difference, but we're thinking of x as a function of y. And that's the region. So now, suppose you wanted to evaluate, say, integral over r of, say, x plus y dA, we get the following. So the y's go on the outside, those are the 0 to 5. The x's go on the inside, those are the left and the right. So the left is y, the right is 2y, the inner is x plus y, and then dx dy. And then that just gets evaluated. So now we'll do a couple more, but I just want to point something out quickly about this region before we go further. So actually a couple notes. So note one is this particular region, it's worth noting, is not vertically simple. Some regions can be both. So a region is simple if it is both horizontally simple and vertically simple. I'll write those the other way around. So I'll give you an example. So if you look at this region, say, oops, let me do that in red. So suppose this is the parabola. We can think of this both as vertically simple as horizontally simple. So as vertically simple, we would just write this as nice and easy. It would be, for an integral, you would have, say, 0 to 3. And then your bottom function would be 0, and your top function would be 9 minus x squared. Then you would have whatever you're integrating, and then dy dx. Now for a horizontally simple region, it's a bit trickier. So what I need to do is I need to think about this function right here as need to solve it for x. So this would be x squared equals 9 minus y. So x is positive square root of 9 minus y. It's positive because it's on the right, it's positive x's. So if I do this as a horizontally simple region, my integral would go 0 to 9 because 9 is now the upper y value, and then the left function is 0. The right function is square root of 9 minus y, and then dot 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 dx dy. So the thing to see here is we've got, these are x values over here, these are y values over here. These are, this is your bottom, this is your top, this is your left, this is your right. Either of these is fine. One you might prefer to the other one. The one on the left is nicer because it doesn't have any roots. The one on the right is not so nice, but there are various choices. And then, of course, note 2 I wanted to make is specifically about this example right here. Is this region is not easily seen to be vertically simple, but can be written as two vertically simple regions. So I'll show you what I mean by that. And I'll show you why it has to be. So if you draw this region again, let me draw it one more time. And I'm gonna sort of divvy it up a bit. The reason is if you want to do it as vertically simple, if you notice what happens here, is that right here, the top function changes. These are different. The bottom function, it's the same. So as vertically simple, we need, or we would need, two separate integrals. One for each side. Integral for this, integral for this. Nothing wrong with it, it's just a little more work. Whereas horizontally simple only needs one, as we see. So the big choice, of course, here is when we're given a problem, we're given a volume, etc., a region, we need to make this decision about whether R is vertically simple or horizontally simple. Once we make that decision, the regular non-iterated integral gets changed into an iterated integral, and then we evaluate. So what I'll do now is I'll do two problems which sort of start at the beginning with a volume question, and then boil it down to a double iterated integral, and then we can go from there. So let's say full examples. So the thing that makes these things sometimes tricky is that the R is typically not given. I need to work it out. So I'm going to worry less here about evaluating the final integral than sort of figuring out from the problem what the R is. All right, so an example like this, let's say find the volume below z equals 9 minus x squared minus y squared, that's a paraboloid, and above the xy plane. Okay. So solution. So take a look at the picture. So I'll draw a few pictures for this. So the paraboloid looks like this. X and y axis like this. Z axis, not the prettiest picture, that's okay. We want that volume. So we need to think about this. Is what is R? What is F? So F is pretty easy because F is the function that we're finding the volume under. So F is the function we want the volume under. So here, f of xy is nice and simple. It's just the paraboloid. Nice and easy, right? The R is the region in the xy plane. So in this case, what I'll do is let me redraw it for you. Again, a couple pictures. So I'll draw it in 3 dimensions and in 2. So in 3 dimensions, the region that we have is this. That is our R. In the XY plane alone, it's just a circle. Now, a couple things about the circle. This is, the circle happens where z equals 9 minus x squared minus y squared meets the XY plane. So this guy meets XY plane at z equals 0, which is x squared plus y squared equals 9. That comes from here, which means this guy has radius 3 over here, right here. So this, again, this is our, let me label things, this is our R as well. So now take a look. We know 2 things. We know our F, and we know our R right here. Sorry, it's kind of sloppy. So those 2 things together will help us see. Of course, what we'll need to do is we'll need to figure out how to describe the R as either horizontally or vertically simple. In this case, it's both, but we'll pick vertically simple because it's a little nicer in this case, as we'll see. So to help us see what's going on, let me just redraw R. We'll say R as vertically simple. At the end, I'll show you what it would be as horizontally simple, but generally, if you can choose, vertically simple is better because it's sort of slightly more what you're used to with upper and lower functions. So like in this case, this is our region. It's radius 3. So if we just focus on R, right, R is inside circle of radius 9. So that gets divided into top function. We solve for y in this case. So y is plus or minus square root of 9 minus x squared. So the plus version is on top, and the minus version is below. So the top is y equals plus square root of 9 minus x squared. The bottom is y equals minus square root of 9 minus x squared. The a and the b, the left and the right here, is negative 3. B is 3. So on the picture, just to clarify, that is our negative 3, that is our A, this is our B, this is our top, that is our bottom. And if we go with that, then what happens is the volume becomes this, right? So the volume is without an iterated integral. It's the integral over R of the paraboloid, right? That's the 9 minus x squared minus y squared dA. So take a second to see that that guy right here comes from this function right here. And then because R is vertically simple, we can rewrite this as negative 3 to 3 of, and then the bottom function, which is negative square root of 9 minus x squared, the top function, which is square root of 9 minus x squared, the paraboloid, this is a particularly icky integral, by the way, and then dy dx. Now, that's sort of the semi-final answer in the sense that that needs to be evaluated, and it's horrendous, but it is an integral. Right? So just to note something, as horizontally simple, I won't show you all the work for this, but it's similar, right? So now these outside integrals are my y values. Y also goes negative 3 to 3. These are now my left and my right functions, so I have to solve for x, and I get negative square root of 9 minus y squared. Up here I have positive square root of 9 minus y squared. Still have the paraboloid. Now dx, dy. For what it's worth, these are the same in terms of values. because you're finding the same thing, but they look a little different because the variables were switched around. But so take a look at this problem and see that you have to sort of dissect it in the sense that you have very little information. You have to reconstruct what the R is, figure out whether the R is vertically simple or horizontally simple. Once you know that, then you get an iterated double integral. So here's one more example. So nice clean screen. So for example, let's say find the volume under the plane. Well, let's just say under x plus 2y plus z. Actually, let's make it 3x plus 2y plus z equals 12 in the first octet. So visually, just so we're clear what's going on here, this plane right here, this guy right here is a plane. We can sketch it by plotting the intercepts, drawing a little triangle. So the x-intercept is at 4. This is not drawn to scale. The y-intercept is 6, and the z-intercept is way up at 12. And so the solid here, or the plane rather, is this little triangle. And the volume that we're looking for, just to be clear, is the volume is sort of hidden under here. So really we're finding the volume of a three-dimensional object, right? We're finding it's like this little wedge-shaped thing. Right, that's not the best picture. Better picture might be like that guy right here, right? So we're finding this volume. Because we're under the plane and we're in the first octet, so we're sort of stuck sort of forward from here. And so again, we need to think about this as a function and a region. So the big first question is, what function are we under? So the answer is the plane, but we need to write it as a function. Right, so we need to solve for z. So this is our f. And so that's the thing that's gonna go in the integral. So we'll do this thing when we know r. So then the question is, of course, what's r? So take a look back at the picture again. So it's pretty easy to see visually. So I'm going to label the 4 and the 6 and the 12. One of those won't be necessary, but that's okay. The r in this case is the region in the xy plane. So the r in this case is this region. So if we draw this in only the xy plane, what we get is the following. In the x direction we go to 4. In the y direction we go to 6. That's this region right here. This is our r. So this is r right here. This is r right here. Those are the same r's. Now, when we look at this r, we can see this r is vertically simple. It's also horizontally simple, but vertically simple is easier, usually. And so what do we need to know? We need to know the left and the right, the A and the B, and we need to know the top and the bottom. Now, a couple of these are easy. The one that isn't is the top. So let's take a look what I mean by that. So in this case, the A and the B are the left and the right. So A is 0, B is 4. The bottom is easy because that's the function y equals 0. That's right here. That's that bottom function right here. The top function, there's a couple of ways you can see it. You can figure it out because you know the x and y intercepts 6 and 4, so you could do point slope or something like that. There's a sort of an easier way. This happens when the plane 3x plus 2y plus z equals 12. This is when it hits the xy plane, so this is when it meets z equals 0. So we can work it out. We can say, so it's 3x plus 2y equals 12. So y equals, well, let's say 2y equals 12 minus 3x. So y equals 6 minus 3 halves x. That is that top function. That's kind of icky. That is that guy right there. Kind of makes sense. It's got a y-intercept of 6 and a slope of negative 3 halves. So, here's the deal. Our volume now is the integral over r of the plane. And as a vertically simple region, the left and the right are 0 and 4. The top and the bottom are 0 and 6 minus 3 halves x. The plane itself is 12 minus 3x minus 2y, and then dy dx because it's vertically simple. And that's the final integral that gets evaluated. So again, this also can be done as horizontally simple, in which case this function, this y equals 6 minus 3 halves x, needs to be solved for x to get it to be the right-hand function. But this is a little bit easier in that sense. So that's the end of the chapter. Hope that was good.